presentation titled "The Weather Isn't What It Used to Be: Separating Fact from Fiction."
Yes, we're good. Thanks, Jack.
Climate. Awesome. Cool. So I'm going to get rolling here. Okay, so thanks again, Juliana, for that awesome intro, and excited to present here. I'll show this slide again just to reorient everyone to where we are now and where you all will be if you attend these sequences of webinars, and then following it into the sort of sector-specific webinars. I think this is a great layout. We're right at the top of the climate science box. So this is the first, I think, I'm the first presenter of a long series of presenters following through this sequence of topics. Full disclosure, I've registered myself as a participant in some of these later ones because I think this is a fantastic overview of things to think about in bringing climate change into the decision making and thinking that you all do out there in the real world. So we'll start out with climate science and get some basic knowledge there. And then in future webinars in this series, we'll move on to these other topics. Okay, so what we'll talk about today between myself and Dave, and we'll be doing some screen swapping, so bear with us on that. We'll start out with some climate change basics, we call it. So really stepping back and thinking kind of at a bit of a global level about what climate change is, how we know what we know about it. But then fairly quickly, the webinar today is going to hone in on not just this big global picture, but really what matters for it with respect to Alberta. And that's the key thing here. So we'll kind of hone in from the global to more of the local, and then close out with some reviews, some of the tools and resources that are available to all of you to understand climate change and how it might affect your decision making and how you can respond to it. Maybe the most important stuff, and then close out with a Q&A and some discussion. Okay, so let's start in topic one, climate change basics. There's the field of climate change, talking about climate change and thinking about climate change involves a lot of words, some of which might be new to some of you, and some of which might be familiar to you, but we might use in slightly different contexts when we're talking about climate change, right? So here's a word map of a bunch of words that you might hear, you will hear more than a few times in this webinar and following webinars. And one of the goals here of this particular session is just to ensure that we're talking in the same language. We're using words, we know what they mean, and we know what they mean, especially in the context of thinking about climate change. So things like climate, of course, models, impacts, variability, mitigation, adaptation. We'll touch on some of these so that the general literacy of what these terms mean is there when you're having these conversations out there in your positions. Okay, so like I said, we'll start kind of at the global and we'll zoom in to the Alberta context throughout the course of this talk. So let's zoom right out and think about the big global picture. Each figure here is actually a map of the world. So if you squint, if you really feel like squinting, you can zoom in and you can maybe see the continents and shapes and stuff like this. But the colors represent something different. They represent differences in temperature between the long-term average temperature of the last century or so, actually last 30 years or so. So there's one takeaway message from here. Don't try and pick out the details. Just look from top left to bottom right. Read these pictures like you'd read the page of a book. And what you see is that over time, there's some red, there's some blue. Red means kind of higher than average temperatures. Blue means colder than average temperatures at that particular place and time in the world. You'll see there's some noise, there's some red and blue, but over time, especially as you get farther from 1850 at the top down to about 2018, year 2018 at the bottom, you'll see, especially starting around 1980 or so, more and more red in the picture, right? And this is just measured temperature out there in the world. And the picture is clear, right? There's more and more warming over time. And this is sort of the basic important signal of climate change. It's warming of the system and all the consequent things that happen because of that. But read it like a book and you can see the picture emerging pretty clearly from natural warmer and colder to more and more warm conditions over time. We can also look at that change in many different ways, many different ways, but this is another nice way to do it. Each circle represents one cycle of the seasons for a particular year, and you can see the years incrementing over time in this animation, right? starting at 1850, sort of back before humans really were influencing the system a lot, and moving forward to the present day. And the thing that emerges in this animation, again, is kind of clear that the circles are getting bigger and bigger with time. And that just shows that for all the seasons, the temperatures are getting warmer and warmer on this big global average, right? This big global average picture of the seasonal temperature cycle. As the circles get bigger, it means temperature is warming, but you also see there's lots of noise, right? Some seasons are kind of cool. Some seasons are very hot. And there's this variability, and this will be an important topic of conversation that we'll have, especially in the Alberta context as we move forward in this talk. Okay, so the system, our planet, is getting warmer and warmer over time, and that's causing a bunch of changes. And we'll talk about a lot of those changes, which are kind of more important in many cases than the temperature change itself. We know why that's happening. That's happening because, particularly, we're adding what are called greenhouse gases to the atmosphere. These are gases, CO2 in particular, but also things like methane, nitrous oxide. What they do is they trap heat on the planet. So as the heat comes in from the sun, which is great, we're happy to have the sun there to heat us up, and tries to get away, some of that heat is kept back instead of being released back into outer space, basically. And that excess heat is what's causing climate change. We see this relationship between greenhouse gas concentrations, for example, CO2, which is the same circles growing on the left, and increases in temperature on the right. So we have the cause and we have the effect, essentially. Now it's worth emphasizing that this is the basic relationship here between greenhouse gases and a warming planet is something that's actually almost going to hit its 200th anniversary of sort of basic understanding. This was first kind of figured out way back in the day by a series of these classical scientists, physicists, who understood it through experiment and thinking that this kind of relationship occurred. So the basic picture behind climate change is not only really sort of settled scientifically, it's been settled for quite a bit of time, and it's an important message to carry forward in the case where you have arguments around whether this is new or uncertain science. The basics of it are certain, and they've been around for like on the order of a couple centuries now, which is kind of cool. Okay, that's the big global picture, right? So we're talking about global average temperature changes over hundreds of years. Let's maybe hone in a little bit on what actually matters for you in Alberta. Well, let's just hone into Canada to start with. These are some plots. I'm just going to move my screen a little bit here so I can see them myself a bit better. These are some plots and figures from a very relatively recent 2019 National Assessment of Climate Change, Canada's Changing Climate Report. This is available online. It's a beautiful summary of how climate and climate change is looking and might look in the future over Canada. So a great resource for you to explore at your leisure. These are some pictures of historical, so past temperature trends up until around the present day for Canada. And we can look at temperature change in Canada in a lot of different ways, right? So climate change, you can come at it from a lot of different angles. So let's start on the top left. This is a picture of average trends, temperature trends in Canada over time. And the warm colors there and the lack of any blues indicate that everywhere in Canada, temperatures are warming over time, over the last sort of half century or so, 7 years, something like that. The other thing, though, to point out in this picture is that the amount of temperature change isn't the same in different places in Canada. Right? So in particular, warming is a whole lot greater in the north. And actually you see that mostly in the winter. Go over to the Maritimes, and there actually isn't a whole lot of warming relative to the rest of Canada. And of course, maybe your eyes will fall to Alberta. It sort of sits in the middle, right? But even in Alberta, there's some differences in the amount of warming that's experienced in the north, for example, versus the south. So there's spatial variability in climate change, spatial variability, and those are terms you can catalog. Let's go down to the bottom left. This is now averaging up each year of temperature in Canada, and then plotting that change over time. So this produces what you call a time series plot. It's just average temperature in Canada for each year from 1948 to 2016. So the same information, same data that makes the map, but just organized in a different way. And here, again, you see a pretty consistent temperature increase over time. So the story matches, right? But you also see that this temperature change isn't constant over time. So if you look at the blue lines, which is the year-on-year temperature, some years on average are warmer than the long-term kind of running mean, which is the black line. And some years are colder, right? So there's time variability in climate change too. And it's kind of a noisy thing, right? Sometimes it's warmer, sometimes it's colder, but the long-term trend is towards warmer and warmer conditions, punctuated by especially particularly warm conditions. So those are the years that often matter, like we just saw this year. You can slice and dice temperature trends in other ways too. You can look at changes in metrics that kind of have a little more relevance to possibly relevance to decision making, right? So you can look at things like the lowest daily minimum temperatures. These are like the coldest days in winter, and look at how those coldest days are changing over time. That's the top right plot. Red arrows up mean those cold days are getting warmer. So just as an example of an indice or something a little more detailed. You can also look at things like growing seasons, the length of the growing season. So it's not a measure of temperature like degrees Celsius or something. It's a measure of days, length of days for a growing season. Same thing here. The message is consistent, right? Like red arrows, the growing season is getting longer, it's getting warmer, so winter is getting shorter. Temperature is one pretty fundamental aspect of climate change. Precipitation, rain and snow is another, right? So let's look at some national sort of scale trends of those. Map on the left, again, map of Canada, but now instead of showing changes in temperature over time, we're showing relative changes in precipitation. Okay, and so maybe the first thing to note here is mostly green, tiny little bits of brown in here, but what the green color is representing is just over time on the annual average. So you add up all the rain and snow you get over the course of a year. It's getting generally wetter across most of Canada, but your eye will be going to Alberta for sure. And as soon as I said that, it's getting a lot relatively wetter in the north. It's pretty dry there to begin with, so that change isn't huge in absolute terms. But if you zoom into different places in the country, you see sometimes quite different pictures. In Alberta in particular, so far hasn't seen a big increase in average precipitation. Dave will talk more about this in the long-term context and what this actually means. But there's lots of spatial variability in precipitation, just like there is in temperature, actually more so. Just like temperature, you can slice and dice precipitation in different ways as well. So the plot on the top right, again, is from Canada's Changing Climate Report, looking at our best estimates of observed changes to stream flow. So just over the historical period up to around 2012, essentially sort of now-ish. And in some places you see increasing average stream flow. So that's the blue crosses. Some places you see decreases. And in other places, you actually don't see any change emerging yet. And that's largely due to the fact that there's lots of natural noise in the system. So you sometimes don't get to see a signal for a bit. But this will be a topic that Dave will touch on in a lot more detail, especially in the Alberta context. Finally, bottom right, the same information on precipitation can be aggregated, averaged up to the whole country. And you can look at how country and national average precipitation, rain and snow changes over time, sort of in this time evolving plot. And picture's consistent there, right? We're generally getting more and more precipitation on the annual average year by year. Okay, so these are sort of pictures of what has happened up to now. And a very important question that, especially as you get into the world of describing climate change to your stakeholders, to people in your organization, is why is that happening? How do we know it's humans and not just something else like changes in the strength of the sun or just natural noise in the system? And especially at the global scale, but also getting down into the scale of provinces and regional areas, we can start to answer that question pretty well and point out quite clearly that the change is largely due to our activities on the planet. So emissions of greenhouse gases and other stuff that we do. And we can look at that and see that particularly clearly by using what are called climate models. And I'll talk a bit more about what those are shortly. But these are essentially computer models where you can do anything you want with them. So you can add humans, you can take humans away, and you can see what the effect of us is relative to a natural planet without us on it by running different types of experiments, simulations like this. And this is one example of this very recent, included in some big new international reports by Canadian authors, I might add. It's cool. The orange line is these climate model simulations with us on this virtual planet, right? The green line is everything as it was naturally, still volcanoes going off, the sun changing strength, etc., but no humans on the planet. And you can see that of those two scenarios, only the orange scenario, in other words, the scenario with humans influencing the system, is able to match the observations of what's happened in the past, which is the black line, right? So this is a way of really kind of adding a really convincing argument to the body of evidence that indicates that we're responsible for a lot of these big changes that we're seeing emerging in the system. Okay, so what we've been talking about so far in this brief intro to this long list of interesting stuff you're going to learn in the next week or so is what's happened in the past and kind of at the big picture of sort of the globe, or at the best Canada. How do we start to understand and project to our best ability to do so how things are going to look in the future? This is super important for decision making, right? You want to understand the system that you're going to have to live in and make important consequential decisions on in the future. So how do we do that? We particularly use climate models. So here's a picture of the past, 1950 to around now, roughly. The thought's not that important. This is the question: what's going to happen next? Decade, 2 decades, even out to the end of the 21st century, which is of importance for a lot of big long-term decisions that are being made now by, for example, people like you. How do we learn more about the future climate? We do that particularly with these things called climate models. And what climate models are, they're really similar actually in many respects to weather models, which we use every day and we make a lot of decisions based on. Climate models are similar to weather models. They're computer models that have relationships built into them that reflect the important things that happen in the atmosphere, the ocean, the land, and snow and ice, sea ice, all the important aspects of the climate system, biology, things like that. So there's these big, essentially computer programs, and when you run them, they give you estimates of what the system will look like in the future if you tell them, most importantly, how many greenhouse gases we will emit into the future. So they're kind of like hazy crystal balls, and you can use them to make estimates of what the future will look like, climate and otherwise. Now, these are computer programs. They run on computers, and they're pretty big programs because there's a lot of calculations that go into understanding what the climate system that you look out your window. I'm looking at my window right now. You look out your window and see that's it's a complex system, and so there's a lot of calculations. All that means that individual climate model simulations of the future take a long time to do, sometimes up to like months of computer time on really big computers like this example. I think this is from the Compute Canada cluster. So supercomputers are used to run these climate model simulations that give us an estimate of what things will look like in the future for various aspects of the climate system. This is actual climate model code. So if you ever want, you're welcome to go and many codes from climate models are publicly available. You're welcome to go and browse through them, and they're super confusing and ugly. There are lots of computer code, and this is exactly what they look like. So this is a picture of computer code coming out of a particular climate model. This is community Earth system model. So that's what climate models are in a nutshell. And that's how we get a picture of what things will look like in the future. These climate models are global because the climate system is a global system, and you can't really understand it at a point without understanding what the bigger picture is. That's just the nature of the climate, the atmosphere, and the ocean, these big things that affect us locally. They're global systems. And to resolve that whole global system in these climate models, you kind of have to break it down into little, what are called grid boxes or bricks that represent different parts of the planet. Here's a picture of a climate model grid, right? So it's not a very pretty looking thing. It kind of looks like 1980s Atari style discretization or pixelization. And so the information coming out of these is great, but it's kind of coarse, right? Like if you zone in on where you are now in Alberta or elsewhere in Canada, you'll see that you're getting information from a grid box that's actually quite large, right? And so you want to make that information finer. The way to do that is to use things that are called downscaling and bias adjustment. These are tools that take that global level information kind of on these coarse grids and use additional context from your location to move those predictions and information from the models at large scales to predictions at local scales. And this is, of course, super important because that local scale information is what actually needs to be used for decision making. So here's a picture. This is a picture of Vancouver. It's not Alberta, but I'm showing Vancouver in particular because it's a horrible place to do this downscaling because it's a really tricky area. There's lots of mountains and oceans right nearby. It's a tricky spot to do this downscaling. But the idea is you take information from the global model and you take this really detailed information on, in this case, topography, makes a huge difference in Vancouver. Same thing can be said for many places in Alberta Front Ranges. And out of those two pieces of information, you get much finer, more detailed information on climate and future climate. And that's a result of global models plus downscaling and bias adjustment, bias correction to move from the global picture down to the local picture. Again, important for decision making. Here's some actual images of kind of downscaling in action, right? So on the background, you see this coarse global climate model grid or pixelized picture of the planet. And we need that again because we need to think about the whole planet, even when we're considering climate at the local scale. And here are grids of zooming in and looking at the same area of the planet, but with downscaling applied. And you see the grid becomes much finer. You get a much better picture of what's going on. It's almost like tuning the dial of your old school TV to get a better picture. It's kind of the same idea. And you can see that you get a better picture of important weather and climate events. This is on the right, a picture actually of downscaled simulated storm that's coming out of this downscaling product that you don't actually get if you just use the global climate model information by itself. So really important workflow from global to local through this downscaling and bias correction methodology. Okay, those are important tools. And you'll hear a lot of climate models, downscaling, bias adjustment, bias correction as you enter the climate change conversation for real. A few other things you will hear about, so we'll talk about these terms now, are concentration pathways or climate scenarios. To understand how things are going to change in the future, we have to know what we are going to do in the future, because especially as you go farther out into the 21st century and beyond, certainly, the biggest effect on the climate is us. So what we do is important. Understanding, especially what emissions will produce in the future, involves creating scenarios of different emission pathways. And these currently are called the representative concentration pathways. These are soon to change. They're changing now because there's a new iteration out called shared socioeconomic pathways. We won't get into details there, but the picture is the same. So these RCPs represent different futures of how humans behave on the planet. RCP 8.5, don't worry about the number for now, is kind of the upper end, sort of worst case, you could say, scenario. This is where there's a lot of population growth. We all burn tons of coal. It's kind of business as usual plus, right? So we don't really worry about climate change at all. This is what climate change will look like if we follow that future scenario to the end of the 21st century. Okay, so it's RCP 8.5. It's a scenario of actually really high greenhouse gas emissions. This is straight from the description of this scenario. You can create scenarios on the opposite side of the story, on the opposite bookend. RCP 2.6 is an example of that, right? This is kind of what the climate would look like if that happened a global scale. You can imagine the real climate sitting somewhere in between those. We're going to be somewhere within those bookends, and that's kind of how you can interpret these scenarios. So these scenarios are used to generate climate model simulations, and you can start to describe the potential range of futures by looking sort of within these two bookends, is one way to think of these scenarios. Okay, so here's today. Black line is like, quote, today, real simple picture of that. Here's the most optimistic scenario, RCP 2.6. The new SSPs, same idea. They'll also be called 2.6. And sort of the worst case scenario, RCP 8.5. here's our sort of today and the bookends of future change. I've drawn these lines out at 2100, but you can draw the same picture wherever you want based on these plots of temperature change for these different scenarios. How do we think and conceptualize of our response, humans' response to this picture? We can think about it in two important ways, and these are really important to keep in mind and to keep sort of conceptually separate, although there's lots of overlap. One way we think about responding to future climate change is through climate mitigation. And then you'll hear that term on mitigation. And that means a very specific thing in the climate change conversation. It means actions to reduce carbon emissions. So we're mitigating the effect of climate change, particularly by reducing our emissions. Climate mitigation means actions to reduce carbon emissions. And those actions are happening now at an accelerating pace. The other way that we can respond to climate change is through climate adaptation. This is kind of taken the story that, well, some change is inevitable. We've committed to actually quite a bit of change already, so we're going to have to take actions to reduce the risks that that change imposes on us. All right, so climate adaptation is really a risk-based thinking to reduce climate change impacts and risks to yourself, your organization, your community, et cetera, et cetera. So climate mitigation is bringing emissions down, and they're related, of course, because if we can bring emissions down, we don't have to spend as much effort adapting. This webinar and my impression of the rest of this series is primarily related to climate adaptation. Right, so we're talking here now about adaptation, risk reduction, this kind of thing. Important to keep in mind, of course, that mitigation is another big picture conversation.
So I'm just going to bring up a polling question here. Which of the following climate impacts is of the most relevance to your work?
Okay, thanks, Jeremy, for that great global and national overview of climate change. Sarah, can you see my screen?
Absolutely, yeah. Thanks, Dave.
Good. Okay, well, given Jeremy's overview, I'm going to scale down to Alberta, focus on Alberta in terms of how the climate is changing, but also the climate impacts. And as Jeremy indicated, we know the dominant cause of current climate change is a warming of the global climate. And so what we observe in Alberta is the regional consequences of global warming. So here is temperature data for Edmonton back to 1900. And it's plotted as anomalies, which are just differences in the temperature each month from what we expect from the average. Red is months that are warmer than average. Blue is months that are colder than average. And as you scan this time series from left to right, you should notice that there is more red and less blue because, especially since the 1980s, there are many fewer cold months and many more warmer months. The warmer than normal months actually are mostly in winter. So if we plot the daily minimum winter temperature every year at Edmonton all the way back to 1880, we see a dramatic increase in minimum temperatures. So this is the lowest temperature each day for December, January, and February, and then it's averaged over the winter for that year. There's lots of variation from year to year, but there's a strong upward trend shown with this red dashed line. If you go off to the left end of the line, back in the day, the average daily minimum temperature was -22. More recently, on the right end, it's higher than -16. That represents an increase in minimum temperature of more than 6 degrees at Edmonton, which is huge. And if you look at the years since 1980, there just aren't many cold winters. Even though we like to whine and complain about winter, and we still get cold spells, we'll still get a week or two of -30, we no longer get an entire winter of -30. And if you scan back The most recent really cold winter was 1969. So we can conclude that not just Edmonton, but this is a phenomenon that occurs throughout the Prairie provinces. They're getting just much less cold. And you can imagine the consequences, both positive and negative, of a warming winter. One in particular that's quite visible is the retreat and wastage of the glaciers, because glaciers grow in winter and they melt in summer. Well, if winter's getting shorter and summer's getting longer, you would expect the glaciers to disappear, which is exactly what's happening. Here's two photographs taken by two different generations of the Vaux family, 100 years apart. The most recent photograph taken by Henry Vaux in a book called Legacy in Time. And you can see how much of the Bow Glacier has disappeared. Bow Glacier is the headwaters of the Bow River. And this is noticeable at Banff because the Bow River at Banff is declining. Now, there's lots of variation from year to year, but that dashed red line represents the impact of a warming climate on the Bow Glacier, and therefore the flow of the Bow River at Banff. Now, if you go downstream to Calgary, and even further downstream, that's not as noticeable because there is other tributaries to the Bow River and to the South Saskatchewan River. And also the watershed gets larger relative to the contribution of glacier runoff. And in fact, that's why there's so much deviation from this trend, is because at Calgary, the contribution of the Bow Glacier is about 1% to the annual flow. Now, in dry years, it's higher. So in the absence of precipitation, the glaciers become more important. But in a typical year, the glaciers have become so small that they're no longer contributing very much to the flow of these rivers. So let's consider precipitation, because that is the dominant source of water, of the water in our lakes and rivers, our water supply. And precipitation that falls as snow is most effective because it's stored, it builds up over the winter and it melts in the spring. Summer precipitation tends to evaporate and is less effective. But this is total annual precipitation at Edmonton. Once again, shown as anomalies, the difference from the average. So the wet years are in blue and the dry years are in red. And unlike the temperature anomaly plot, there's no pattern. There's no decrease or increase in wet and dry years. Rather, there's a lot of variability from year to year. Precipitation, it's almost like whiplash. We have wet years and dry years. And in fact, we have wet decades and dry decades. If you look at the 1990s and early 2010s, you can see a lot of red bars, a lot of dry years, and relatively few wet years. And as a result, there was a series of dry years in central Alberta. Now, just like the glaciers are an indication of snow accumulation, the lakes in Alberta are an indication of the annual water balance, especially the shallow lakes in central and southern Alberta. They retreat and expand in response to snowmelt and precipitation. So you can see we had a bunch of dry years in central Alberta, ending in about 2008. Well, in 2008, I was giving a talk in September in Sherwood Park. And after my talk, I went for a drive and I went over to Cooking Lake. I tried to find the duck blind that my dad built and where my dad, my brother, and I used to hunt ducks and geese on Cooking Lake. I couldn't find the duck blind because I couldn't find Cooking Lake. In response to those dry years, Cooking Lake had retreated. You can see in the background some homes that have been built in the 1970s, probably, on the shoreline. Then the lake began to retreat. Somebody moved their dock out towards the lake and eventually gave up because they could no longer access the lake. Well, since then, there's been wet years and Cooking Lake has come back, just like a lot of lakes in Alberta have risen again. But they will fall because we get this decadal cycle in precipitation and water levels on the prairies. And it tends to hide the impact of climate change. It's difficult to see the impact of climate change on precipitation and water levels because of this year to year and decade to decade variability. But we know that the climate is changing, and the signal is quite clear in terms of precipitation. Sorry, the signal is quite clear when it comes to temperature. And this is a plot that Jeremy already used, showing the historical change in temperature up to about 2010. And then beyond that, these are projections of future temperature according to the different RCP scenarios. So I won't repeat what Jeremy clearly said about how we expect temperature to change in Alberta according to the anthropogenic or human forcing of the system. But I want to point out that a lot of that extra heat is being stored in the oceans. Because after all, 3/4 of the earth is ocean. North America, Turtle Island, is surrounded by water. Our weather tends to come from the west, so our water comes from the west. It comes from the Pacific Ocean. And this image taken from space captures really nicely how the weather is passing from the subtropical Pacific Ocean and over Western Canada. Because those three swirling cloud systems, there's three of them, those are air masses, low pressure, we call them cyclones. They're forming over the ocean and they're bringing water to Western Canada. And as the ocean heats up, there's more evaporation. As the air heats up, it can hold more moisture. And that's why we expect actually there to be more precipitation in Western Canada in the future. However, those storms don't necessarily come to our part of the world. They did on this particular week, as shown here. But these storms could take a trajectory that takes them over the US or further north. In that case, we have a lack of precipitation in Alberta, but higher temperatures. And that's what we expect in the future there to be, we expect dry conditions to be drier and wet conditions to be wetter as a result of the warming of the climate. What I've shown and discussed really are the incremental and sort of slow onset changes in the temperature and precipitation. But the other aspect of climate change, of course, is the change in the frequency and the severity of extreme events. And this is probably the more ominous and more challenging aspect of climate change, is the change in not just the trends, but the change in the variability and especially extreme weather events. Well, Alberta actually already is a land of extremes. And here's a way to explain that. This is just generic data. It's not necessarily from Alberta, but it's a whole series, time series of winter precipitation from 1950 out to the end of the 21st century. And the first 30 years and the last 30 years are shown. We're somewhere in between. And the way to think about it is using the first 30 years, and this is probably daily data, because if we're talking about extremes, we have to measure precipitation on a daily and hourly basis. So in 30 years, we have a pretty good sample size of hourly and daily data. And here in green is the level at which winter precipitation occurs 1% of the time, 1 in 100 years. But as a result of the rising winter precipitation, the last 30 years of this century, that 1 in 100-year winter storm is of much greater severity. So there is a change in the intensity of the extreme events. Choosing a single probability, 1 in 100 years, but examining the shift in the intensity of these storms. Or we could take a different approach. We can keep the severity the same and look at the change in the probability. So the green bar on the left and the green bar on the right are at the same height, representing the same amount of winter precipitation. But in the future, this amount of winter precipitation will occur 1 in 20 years, 5% of the time, not 1% of the time. So there is a change in the frequency of these extreme events. I need some coffee. So that's sort of a generic way of thinking about it, conceptualizing it. But here's some actual data from Alberta. Number of wet days at Red Deer, 10 millimeters, 4 inches of rain at Red Deer, and the number of days it occurs each year. There's the historical data in gray and black, and then the projections according to different RCPs in the future, starting around 2010. And if you follow those solid curves, there's a slight rise in the number of wet days, representing an increase in precipitation. But rather than looking at the running mean, look at the actual data, the shading, and you can see how the range of number of wet days increases over time. In the future, the dry years will actually be drier than the past. So there is 1 year in the future when there's only 2.5 days of 4 inches of rain at Red Deer. Conversely, there's a day in the future when there's 22.5 days of 4 inches of precipitation. So that expanding range of heavy rainfall is the more challenging aspect of climate change than rather as opposed to just the gradual increase in the wetness of our climate. Alberta already has Canada's most extreme climate. This is the 10 most costly weather disasters in Canada since 1983, and 6 of them occurred in Alberta, and fairly recently. Of course, the Fort Mac fire was the most costly weather disaster in Canada, but also there's the flood of 2013. Then there's other floods and fires that make the top 10 in Alberta. Now, keep in mind, these are insured losses. So what doesn't appear is drought, because so much of the impact of drought, especially on the ag sector, is uninsured. But if you consider the total cost of extreme weather, you can argue that drought is actually the most costly disaster. Because after all, floods and heavy rain affect people and industry in low-lying places, but drought eventually affects everybody. Initially, drought affects agriculture, but if drought persists for a year or more, eventually it affects everybody because it affects the water supplies for municipalities and industry, et cetera. Okay, so Alberta's already got the most extreme climate, and as a result of an increase in heat and precipitation, we expect even more extreme weather. Now, what's not shown here is a hailstorm that occurred last year, which probably would appear on this list, and the heat wave of this past summer of late June, which affected more so BC. And that heat dome triggered some international research on what's called attribution research. And a group of international climate scientists got to work immediately and demonstrated that that heat wave and those high temperatures would be virtually impossible in the absence of global warming. Something else that's characteristic of Alberta and the Canadian prairies is the variability in water from year to year. This is a map of the world showing the coefficient of variation in what's called the climate moisture index, which is the difference between precipitation and the loss of water by potential evapotranspiration. So it's how much water is left over after plants transpire water and water evaporates from the soil. And the coefficient of variation is just a measure of the variability from year to year. So most of the world, the coefficient of variation is less than 25%. But the areas that are colored, and I won't tell you why there's different colors, but anything in color is a variable climate. Throughout most of the world, this climate variability occurs in the transition between wet and dry climates, and it's a fairly sharp transition. But in the interior of the large continents, like in the interior of Eurasia, in Kazakhstan, Mongolia, Western China, there's a large area of variable precipitation. But on the northern Great Plains of North America, which is the geographic center of North America, there's also a large area of variable precipitation. So the Canadian prairies share the distinction with Kazakhstan and Mongolia as having the largest variation from year to year in climate moisture. And it's only getting larger as a result of climate change. Well, here is what's called a scatter plot, a scatter of points, showing the change in precipitation on the vertical axis and the change in temperature on the horizontal axis from between 30 years in the recent past and 30 years starting this year and up to 2050. Each of those symbols represents a climate experiment, a climate model simulation. Now, if we were talking about a fairly consistent and benign climate, you would expect some kind of consistent pattern. You would expect some kind of clear pattern, but we're not dealing with a consistent climate. We're dealing with the climate of Alberta here. And so there's a large amount of scatter. Every symbol represents a different climate model simulation, and they're all over the place. And you can see that using two different greenhouse gas emission scenarios, there's also a large scatter, but there's also a large amount of overlap. So what we conclude is there's a large amount of uncertainty here because we're using different models and two different greenhouse gas emission scenarios. So those are two sources of uncertainty. So why don't we just use one model and one RCP? Okay, well, we ran that experiment in our lab at Park. We used the Canadian Regional Climate Model, which is the downscaling of the global model to Alberta. And we used a single RCP. And we projected precipitation and temperature for the near future and for 30 years starting in 2051. And what do we get? We get a big scatter of points. Even though it's a single model and a single RCP, there's still a large amount of uncertainty. And the source of that uncertainty can't be the models, it can't be the RCP, it's the internal variability and the large natural variability of the climate of Alberta. So something else we did at Park, I collaborated with Dr. Elaine Barrow. She did most of the work. And we said, okay, how much for the Canadian prairies, how much of that uncertainty can we attribute to the natural variability, to the climate models, and to the greenhouse gas scenarios? And this is what we found for seasonal precipitation. Nearly all the uncertainty is just the large internal variability of the regional climate of Alberta. The models, the different models contribute a lesser amount of uncertainty and a relatively small amount of uncertainty, and not till later in the century is the result of using different greenhouse gas scenarios. Now be careful how you interpret this. It doesn't mean that the greenhouse gases aren't important. They're extremely important, especially for temperature. But I'm only showing you the projection of precipitation. And the take-home message is, on the Canadian prairies, we have a very challenging climate to model future precipitation. And that when we interpret the future projections, a large amount of the discrepancy between the different projections of precipitation is a result of just the large natural variability. And here you can see it. I mean, this isn't the future, this is the past, and this is recorded. This is the flow of the South Saskatchewan River at Medicine Hat from 1912 to 2016. Once again, it's anomalies, which is a really nice way of looking at data. Blue years are high flows, red years are low flows. A lot of whiplash from year to year, but quite clearly decadal variability. 1 or 2 decades in which the river was low, like the 1930s and early 40s, and several decades in which the river was mostly high, like the 1950s, 60s, and early 70s. And then it flipped again. And we attribute this actually to the circulation of the Pacific Ocean, something called the Pacific Decadal Oscillation. The year-to-year variability we attribute to El Nino and La Nina, because after all, this is where most of the water is coming from the Pacific. Well, even though there's a fantastic record of more than 100 years of the flow of the South Saskatchewan River, it's only capturing several cycles that are more than a decade in length. So in our lab at Park, we've devoted a lot of effort to trying to extend this river flow of the South Saskatchewan River, and we've been able to extend it back to the year 888 and up to 2019. So if you've got a 1200-year record of the flow of the South Saskatchewan, you clearly see these decadal cycles. But what you also see is what the gauge has been recording is a relatively less drought than in the past. Because if you look at the last 100 years in this record, there's lots of drought. There's the 30s, the 80s, and so on, the 2010s. But we already know that from the instrumental data. But if you go prior to the installation of the weather and water records, you can see long periods in which the river was low and stayed low for decades. This isn't a model, this actually happened. And the most challenging future climate for Alberta will be not if, but when one of these decade-long droughts reoccurs, but in a warmer climate than in the past. This information, by the way, is from trees, because trees like this 1,000-year-old limber pine need water, especially this tree, because it's growing in the whaleback south of Calgary on rocky soil. And when you look at a core of this tree, a core about the size of a pencil, if you cut it open and sand it, you can see the year-to-year variability in the tree. And in our lab, we measure to within a micron the growth of the tree, and it correlates quite nicely with water levels for the last 100 years. And so we can extend it back to the year 888. So the takeaway in terms of the climate of Alberta is that the climate change is both long-term incremental changes, like trends in water levels, temperature, and precipitation, but also shifts in the intensity of extreme events. Now, global warming doesn't create these extreme events, but it amplifies their severity. And if you define an event as having a certain severity, so if you define a flood or a drought as a certain amount of water, then that level will be exceeded more often in a warmer climate. So here is a way of thinking about that. This is actual data for the prairies. This is summer precipitation, and it's plotted as a bell curve with the probability between 0 and 1 on the left, and the amount of summer precipitation on the horizontal axis in 3 30-year periods, green in the past and blue and red in the future. And there's not much change in the average value. It's shifted a little bit to the right. So there's a little bit more summer precipitation, but not a lot. And it'll all be lost by evaporation. So it's not getting wetter in summer. But the thing to note is how these curves are being stretched. The tails are getting longer. So the most important information, the biggest takeaway, is that the left tail is getting longer, which is drier conditions, but especially the right tail is getting longer, which is those wetter months and years. And then in the last few minutes, just want to say a few things about how we expect these climate changes to impact Alberta. I'm taking this information from this report, the Prairie Provinces chapter, in the report, Canada and the Changing Climate. This chapter was released in December 2020. There will be a chapter released for every other province and territory in the coming year. The Prairie Provinces got off to a quick start, so our chapter is published. 15 authors. And we had several key messages. First of all, in terms of ecosystems, that as a result of a warming climate, the ecosystems are shifting. For example, we expect the boreal forest to retreat to the north and the aspen parkland and the grassland ecosystems to expand. And that's shown here. The author of this section of the report is Rick Schneider from the U of A, and he wrote a report in 2013. And they had a map of the distribution of Alberta's ecosystems historically on the left, and in the future, when you apply a global climate model to the what are called bioclimatic envelopes, the temperature and precipitation that is characteristic of these different regional ecosystems, you can see the expansion of the grassland and the aspen parkland and the expansive forest, both in the north and in the west. And the west, of course, is the Rocky Mountains. And I took this picture from the whalebacks while those students were coring a limber pine. I took this picture, a whole complex of ecosystems. There's this elevational zonation from the fescue grassland and montane forest in the foreground, right up to the subalpine forest and alpine in the distance. And with the warming climate, all of these ecosystems are shifting to higher elevation. The alpine ecosystem eventually will run out of room, and on some of the lower ecosystems, on some of the lower mountains, the alpine ecosystem could disappear. Then in terms of agriculture, if winter's getting shorter, then the growing season is getting longer. And so we documented benefits to prairie agriculture. However, producers can take advantage of these warmer, longer growing seasons only if they can deal with the impacts of climate extremes. And not only is a warmer climate good for plants, but it's also favorable for pests, vector-borne diseases, and invasive species. Here's an indication that already the warmer climate is benefiting agriculture. This is forage yield data from pasture land, from Agriculture Canada at 1.4 Alberta. And you can see that pasture productivity has been rising since the 1980s. Even so, of course, there's still years when there's not enough water. So we still have problems and always will have problems dealing with dry years, despite the availability of more heat. And then this section that I wrote on the amplification of extreme events by a warming climate, which you can argue is the most challenging consequence of climate change on the prairies. We're already seeing the increase in the frequency and severity of flooding, drought, and wildfire. And some of that increase has been attributed to climate change. This is work we've done at Park. My research associate, Rayhan Anis, work we've done for EPCOR, modeling the flow of the North Saskatchewan River at Edmonton out to the end of the century. If you follow the solid line, on average, the river's gaining water, not a lot, but some. But the thing to note is the variability from year to year. So the challenge lies in dealing with this large increase between the low water levels, which are just as low as in the past, but much higher water levels in the future. And using the same data, Rayhan plotted two hydrographs, the future hydrograph in pale blue and the historical hydrograph, the baseline in dark blue. And you can see how the entire hydrograph is shifting to earlier in the year. It's actually more water, but the water is arriving a month earlier and it's arriving in spring and winter. When you get into summer, there's actually quite a bit less water in the river than in the past. So therein lies the challenge. Even though we might have in total more water, it's the shift in the availability of water between months and between years, and the increase in the range of water levels in the future that's going to require quite a bit of adaptation. And finally, last slide. Our social scientists, led by Deborah Davidson from the U of A, point out that any kind of change, any kind of stress is always mostly disadvantageous to the most vulnerable people in our society. And that's clearly obvious, for example, with the COVID pandemic. So we can expect that social inequities and vulnerability will be exacerbated for Indigenous people, women, poor people, the youth, the elderly. And that public policy and adaptation has to consider their vulnerability, but also some of the unique strengths of these social groups, and also the intersection of race, age, gender, and poverty, and how that amplifies vulnerability.
We'd like to know where you get most of your climate information. Is it the news, social media, academic articles, friends and family, the IPCC, or is it not captured here?
We're going to close out the last little bit of this session with a really brief review of some tools and resources that you all have now available to you to start to explore climate change at the Albertan scale, and even honing in regionally and locally to get some information on climate change trends, this type of thing that may be important for you to start thinking about how to bring into your planning and adaptation. The first place to look at, worth highlighting, is just the evolution of national codes and standards. So a lot of things that get built here in Canada in the infrastructure context are built according to codes and standards, which is a good thing. And a lot of these codes and standards, the initial sort of version of them is developed at the national scale and then modified over time by provinces, territories, et cetera, to meet their local context or the regional context. And so because these codes and standards are sort of these foundational units, there's a lot of work now going on to update them to include the impacts of future climate change, and in particular, including measures of weather and climate coming not just from historical observations of these things, but those combined with future projections from tools like climate models. The Climate Resilient Buildings and Core Public Infrastructure is a recently concluded big national project working to address this type of thing for the National Building Code of Canada and the Canadian Highway Bridge Design Code. And so the goal of this type of project and ongoing projects that are following from this is to bring climate change information into these model codes at the national level. So ideally, in some years from now, we'll start to see the emergence of real sort of minimum codes and standards that include climate change, in descriptions of how to make things like buildings, bridges, roads, big expensive things that last a long time, and therefore we'll see a lot of climate change over their lifetimes. There's also more and more policy and plans afoot, again at the national level, and we'll go into Alberta in a sec, but to bring climate change considerations into funding models for a lot of things, including in this case, again, infrastructure. So programs like the Climate Lens, which essentially mandate a climate change risk assessment adaptation plan as a part of application for the hundreds of millions of dollars needed to build big expensive things that last a long time, like highways, like airports. Here's an airport where the permafrost underneath it is melting away, and you can see the drastic impact of that on the runway itself, right? So there's funding considerations now that really ask for some climate considerations as part of the money. So there's lots of sort of emergence of, let's say, federal level policy funding streams, this type of stuff that include climate change considerations in them now, and you can learn actually a lot about what's necessary by exploring those in the course of your work. Where do you actually find climate information that you can use in those types of exercises? There's a continuum of climate portals at the federal level, the national level now, that you can go to and find climate change information for your location. One example of that is the Climate Atlas of Canada, and there's a URL link there. A great, really wonderful, user-friendly, easy to use site where you can actually go and get your own climate data, right? For various ranges of grid sizes from 30 to 60 kilometers down to actually some specialized narrative style projections for actual major cities and locations across Canada. So Climate Atlas of Canada is a great place to explore changes in temperature and precipitation for lots of different measures of temperature and precipitation, extremes, averages, things like this. On the same spectrum is climatedata.ca, which is developed by the Canadian Centre for Climate Services, which is where I sit in Environment and Climate Change Canada. It's developed with a lot of partnership from a lot of other folks across the country. Same type of thing, but a little bit more sophisticated. You can go and actually get climate data for a bunch of temperature and precipitation indices, and increasingly other things that you can use to bring into your climate change risk assessment, climate adaptation planning, right? So especially things that have some relevance to decision making. So for example, IDF curves are an important thing for a lot of thinking, especially in the infrastructure world. We're working to serve those historically, and even in the near future, serve future versions of those. So we're trying to hone this information to make it decision relevant. I said I worked for the Canadian Centre for Climate Services. This is generally an organization that's mirrored by regional organizations across Canada. You'll hear about the Prairies version of that shortly. That works to translate climate information, climate data through to decision making. There's URL links here. We have, let's skip ahead. You can find us on the web. I will note, possibly at my peril, we have a really unique service, which is a support desk with a phone number and an email. But if you call that number, you'll be patched through to a climate services expert. In some cases, that might be me. So it's a real interactive way for you to start to ask those questions that need to be asked about what climate information is relevant to your decision making. Canadian Centre for Climate Services. I'll turn it over now to Dave to hone in a little bit more on the Alberta context and describe what some tools are available there.
In addition to those great data portals and websites that and resources that Jeremy mentioned, of course, the Alberta government has their own service. Just like I mentioned that Alberta Environment and Parks has the capacity to do climate modeling and downscaling in the group in Calgary. There's also something called the Alberta Climate Information Services that I expect most of you are familiar with, but if not, it's a really great tool that's got over 10,000 maps of Alberta weather and climate. and a lot of station data for about 350 weather stations. And so these maps and data describe Alberta's weather, climate, and with a focus on agriculture. So I'll make you aware of that. But I also want to make you aware of Climate West. And there's already been a reference to Climate West because Climate West will be the archive, will be the repository for all of the art presentations are being recorded, and they'll be accessible at the Climate West website. Climate West is a new nonprofit organization. It's a regional hub for climate services in the Prairie provinces. It provides access to prairie-specific climate information with a mission to empower people, communities, businesses, government, et cetera, to address climate risk with the focus on adaptation planning and response to climate change. And it's part of a national network. So the Canadian Centre for Climate Services was established by Environment and Climate Change Canada. And so before Climate West was created, there already was regional hubs, PKIC serving BC and Yukon, RANO serving Quebec, and then Climate West was established. And since then, there's been a hub established in Atlantic Canada. So we're just going to give you a few key takeaways here from what we were presented. And first of all, the fact that human-caused climate change is very well documented. As Jeremy mentioned, there's research going back 200 years and on the connection between the chemistry of the atmosphere and the temperature of the atmosphere, and that the science now is well established. The IPCC, which just released a few weeks ago its 6th assessment report, describes global warming as unequivocal. Difficult to say, but it has a lot of impact, that particular expression. And that there are significant, not just future impacts, but present day impacts of climate change. And they will continue until carbon emissions fall to zero. So Jeremy mentioned that we expect anthropogenic climate change to be with us for centuries. We depend on climate models, downscaling to finer scales, and bias adjustments to provide estimates of future climate conditions. We have no data for the future, so that the models are the only reliable source of information about the future. And these models are run or forced with various greenhouse gas concentration scenarios, those RCPs, which have now transitioned into SSPs. Climate adaptation and mitigation are two ways for society to respond to climate change. And Jeremy used that really nice diagram to show the distinction between adaptation and mitigation in terms of the projected changes in temperatures and what we do about it. And that, as our last few slides demonstrated, there are various websites and a lot of resources that are readily available for your information and in support of decision-making in your sector and in your industry. That's it, thanks.
And we'd like to know what the most interesting concept that you learned about at today's session is. See downscaling popping up quite a bit here. Variability, modeling, adaptation. Awesome.